All right, good morning, everyone. This is seminar 2 of the quantum computation series. Last time we covered some bare basics of quantum computing. We talked about what a qubit is, what superposition is, how we can represent multiple states at once, superposition, as well as entanglement, how we can link two qubits where they respond the same way to computation. This is seminar 2. We're going to start talking about some of the algorithms available with quantum and go into how they can be applied to AI. Now, we're not implementing quantum AI yet. That's the next seminar. But I'm just going to introduce some of these quantums, things like Grover's algorithm, which are just instrumental for AI with quantum. So we have those key principles. And for anyone who's just joining this seminar, superposition is where instead of being in a state of 0 or 1, we have a qubit that's simultaneously in all states between 0 and 1. It's a probability of 0 plus a probability of 1. Okay, and that allows us that instead of testing 1 out of 2 to the n possibilities with n bits like we would on a classical computer, we can test all 2 to the n possibilities at the same time. Then we have some entanglement. What entanglement is that we perform something like a controlled knot operation. We link 2 qubits. This allows us to be able to perform computation on one qubit and measure the other. It's important because you can't copy a qubit. Okay, to copy a qubit, you'd have to measure it. If you measure it, it'll collapse at superposition state. You can't copy it. Interference, phase, and amplitude. Now, for this seminar, I've said I'm not getting too deep into the math, but a lot of these algorithms work because, I don't know if you remember, we had that block sphere that represented the North Pole was 0, at the South Pole was 1. But you also have I and negative I, and then the positive and negative directions, the positive ket and negative ket directions. And what we're doing is with phase, we're rotating that vector around that sphere. And then with interference and amplitude, we can increase the amplitude of the solution that we are looking for. So like when we do a search algorithm, we actually rotate the phase of the desired outcome to increase its amplitude around the mean. I know that's hard to conceptually understand. On the GitHub, I have a video link that does a better job of explaining with graphics and visuals. It's really good. I kind of think that Grover's algorithm is magic. Then the potential from speed up, I already talked about that a little bit, that instead of testing 1 out of 2 to the n possibilities at a time, we test all of them at the same time. And so, for instance, with Grover's search, and we'll talk about this in a minute, we take, if you're searching an unstructured database, what's the complexity there? Oh, well, if you're just searching, there's no structure to it. At the worst case, you have to search every single entry. You have to search n entries. With Grover's algorithm, it's actually the order of square root n, to be certain that you have. So, I mean, and it's one of those things where, you can understand how that scales. Let's say at 100, you just have 100 entries. The O for a classical computer is 10,000. Okay. Or I'm sorry. If you have 10,000 entries, the O is 10,000 for a classical computer, whereas 100 for a quantum. Grover's search algorithm. All right, this is fundamental. Most of your quantum algorithms that you're going to encounter, especially on the AI computation side as opposed to the cryptography side, are going to use Grover's algorithm. Okay, there's 2 basic components to Grover's algorithm. You have what we call an oracle, which marks the state we're looking for. Then you have the diffusion operator. Okay, and so what this does is, let's say we're looking for a specific state. We mark that with the oracle. This is the state we want. And then we perform rotations in the this diffusion operator where we find the specific instance that we want. And the video does so much better, but let's say we start here at this S position, and we're trying to find omega. Basically what we do is we rotate the phase of the desired one by half of theta, and then we perform a rotation that brings us closer. And after square root n operations, roughly, we will actually align that S that we're looking for with that omega. And this is a big hyperparameter thing. Anytime we're conducting a search in quantum, most of the time we're going to use Grover's search algorithm or some variation of it. This variation searches for one entry, but we're also able to search for multiple different entries or multiple entries of the same. If we're searching for 4, we can find all instances of 4 with different variations. Now, bear with me on this. So I implemented Grover's algorithm on IBM system. Okay, and the layout's great. Let me see if I can turn off the lights up here. All right, that should be a little more visible. So over here, I have my basic code implementing Grover's algorithm. Okay, and so I write my code over here. Can all these Zoom things please get out of the way? There we go. So I write my code over here, and it implements my qubit gates. So it starts with a Hadamard gate that puts all the qubits into superposition. All right, then I have my diffusion or my oracle right here where I'm marking that I want the 0-1 state. I then reinforce the superposition, and I perform rotations to mark that I don't want these positions. Now, here at the bottom, you have to realize that just as with a traditional computer, you can optimize a circuit, IBM takes care of that for me. So I say what I want, and it optimizes it not only just from pure optimization, but also on the specific quantum computer I'm working on. They'll have different parameters, different things that'll work best for them. And so it uses some different gates down here than we normally use, some square root, some RZ gates, but it handles the optimization for me. All right, and so here we can see that the simulated values. I know it's a little hard to see for you guys, but hey, we're going to find 1-0 with 100% probability. The amplitude rises to 1, But over here I have the actual quantum. And because of the uncertainty, you can see that there are a few samples over the 256 runs I did that have emerged as 1-1, 0-1, and 0-0. However, it's pretty clear that we found the 1-0 state. And you have to understand this is a probability. Let's say it's 95% probable that I found a 1-0 state. There's 5% that it actually could be one of those others.
In terms of optimization, resource allocation versus the performance in terms of the correctness of the job.
Yes.
How do we make a balance between resource
Yes. So there's multiple aspects to that. With the one is there is quite a bit of resources available with understanding noise. There's I believe lead-lad operators, where basically you can understand the uncertainty in your quantum system and you can dial how much certainty you need. Now, like with Grover's algorithm, you can actually kind of deterministically determine how many operations you need, because we're rotating towards that omega vector, okay? And there's a proof that shows that you want that. It's actually pi times the square root of n over 4. But for that, that's going to optimally align your vector with that omega vector. After that, you'll start dancing back and forth around it. But you're going to basically, based on the number of qubits you have and the operation that you're doing, you'll need to understand what probability do I require for this. And it's one of those things where more runs, more error correction, more fault correction will increase that probability, but you have to balance that with cost. And with quantum, you're always going to want multiple runs because it's an uncertain. It has more of the element of chance to it. And so you'll have to dial, do I need to be 99% certain? Do I need to be 99.9% certain with how many repetitions you do?
So we have to do trial error, or is any learning algorithm available?
Yes, no. There's actually just straight like Bayesian probability and variations of that with the math that you can calculate basically your uncertainty, and you'll have to include in that metrics from the specific quantum computer you're working on. And IBM does provide that. They provide how often basically decoherence or faults occur in that system. So you take the fault of the system and you plug that into your probability to understand how many runs you need for a certainty. Okay. You have some? No? Okay. All right. So any of the engineering students in here will be familiar with the Fourier transform. There's a variant of that for quantum called the Quantum Fourier Transform. You know, in your traditional Fourier transform, you have a complicated wave. Has, you know, multiple peaks, and it drops and different peaks. Well, the Fourier transform allows you to decompose that into a series of pure sine waves. Okay, this wave plus this wave plus this wave comes together to form this wave we're talking about. Now, there's also a discrete version where we take a continuous function and we decompose that into a series of discrete variables. And this is the quantum version of that. And I was honestly surprised as I started getting more and more into AI, how often you can represent what you're doing as a frequency wave, you know, of how these things occur. And so with that, oftentimes you're going to want to decompose this frequency variable that you're working with into a series of discrete things. And so what we have is, you know, we have all our possible test inputs. Okay, we provide a Hadamard gate, a 90-degree rotation, another Hadamard gate, and we narrow the field. And we continue to do this until we decompose it into the elements that we need. And so, I mean, this has a lot of application with graph neural networks. Right now, our graph neural networks are largely convolutional in nature because graphs are really information dense. We need to sample that down to a smaller size that way we can work on it. Now, like theoretically, we would not want to downsample. Generally, there's going to be information loss there. We're not going to have as exact an answer as we would like. So with that, if we don't have to downsample with a graph, what we can do is things like spectral techniques. You take the eigenvalues and eigenvectors of the adjacency matrix that represents that graph. Okay, you turn that into a spectrum, which is basically like a frequency wave. And so with that, you can then use the quantum Fourier transform to understand aspects of that characteristic wave. Up here, I have some of your gates that we use. And over here is what you'll probably see in a mathematics textbook. But with that block sphere and the qubits, we basically have this basic gate where we have rotate this value by 1, rotate this value by -1, rotate this value by I to accomplish that decomposition. It's used a lot with signal processing, I always said, but as well as cost function optimization. Okay, so you might have a cost function for during these periods when I operate this piece of equipment or whenever I'm transporting this loads, it costs this much, this period it costs this, but I have this complicated like traveling salesman search problem, like in logistics, where, hey, what route should our trucks take to solve something? And this has been usually an NP hard problem. You know, that, hey, you have to exhaustively brute force search this system to try to find the optimum. Quantum provides a way for us to efficiently solve those kinds of problems. That's why it's being used a lot in logistics. It's why it's being used a lot in hyperparameter optimization, because we can efficiently solve these systems where we can test all possible states at the same time. Some other quantum algorithms that are really important for AI. We already talked about Grover's as well as the Quantum Fourier Transform. And then you have QAOA. That uses elements from the Quantum Fourier Transform to conduct optimization. It's used a lot in AI. Variational quantum eigensolvers. Okay, so with AI works by gradient descent. Go down the hill till you can't go down the hill anymore. Okay, but what's the problem with that? Well, smart people in here and Dr. Lowe's flat.
Shallow.
Local minima, right? Local minima. You get stuck somewhere. So that's a non-convex optimization problem. There are hills and valleys in your thing. So with the variational quantum eigensolvers, we can actually evaluate the entire state space at the time, provided we have enough qubits, where we can actually find the global minima instead of the local minima. And if any of you have implemented AI, you run it, you try to inject heat or noise into the system. That way you avoid those local minima. You start from different, starting points. You play with your learning values. But, we've seen how difficult that is whenever we start getting, 10, 100, 1,000, 10,000 variables on solving these non-convex optimization problems. And then quantum walks, okay? A lot of times graphs are too computationally expensive to take as a whole while you're working with them. So a lot of times we do what are called random walks through a graph. Hey, instead of taking the whole thing, we sample by going from one node to the next, to the next, to the next. The quantum algorithm has methods in it that allow us to efficiently survey neighborhoods of the graph, where we can get a fuller understanding of what's going on there. All right, and then you have QSVM. All right, so that's the quantum support vector machine. Okay, we know about support vector machines in AI, but with this allows us to speed up this classification machine learning task. Okay, where maybe we're not implementing a normal deep neural network, which I talked about last time, how it's a little inefficient, especially in this NIST era, to implement on a quantum computer. But SVM is a much lighter, leaner model, and that's actually possible to be implemented.
The control for the global algorithm is mainly for the speeding up, or do you see that any additional advantage?
So
if times faster?
I believe that's an exponential speed up. I think that's from like cube to linear. Yeah.
You also see that on the AI part, we also evaluate based on the existing system.
Yeah. And that's the thing. So we're in that NIST era. We got 1,000 qubits. I was telling someone before, if you think about that, that's 15 N64s. Round. So we don't have a lot of capacity right now. But if you can fit your problem into a quantum solver, it is much, much faster, and it can find the better global minimum. Yeah.
This question's been kind of itching since like the first seminar, where would we still do some detective work on whether it can give us the best parameter? We still have some detective work for it, because would that automatically also include anything that would be overtraining the model if we just look for the best?
Yeah. So as I said, you could use this as a layer in a deep neural network, where you return a value, but we're not going to want to put a deep neural network in it. But if you can fit your problem in the amount of qubits you have, it's going to basically eliminate that guesswork. Now, in this NIST era, what we're going to run into, though, is we're probably going to convolve or reduce the size of our sample, then hand it to it. And with that, there is going to be a little bit of that guess detective work, based on what layers of convolution, what features you select before you pass it to the quantum computer. So there is going to be some indeterminacy there. Yeah. All right, and here I just quickly charted some of the values here. So for matrix inversion, if you've had linear algebra, you know what a pain it is to invert a matrix. And the same for computers. It's a super costly, expensive function. Like in numerical optimization, we know that if we know the inverse of a matrix, of a quadratic function, we can just immediately solve for the answer. Okay, but that inverse is so expensive. Okay, so we have to use different algorithms to try to find that, or approximate it, or perform our walk. But with matrix inversion, with a classical computer, you're dealing with a cubed function, and with quantum, you're dealing with an n log n function. Much, much more efficient. And then for the search, I already talked about that. With classical, it's going to be linear. You're going to have to search n samples. But with quantum, you're dealing with O of root n. So that much, much faster. Now, it's the balancing act right now that we're in that NIST era. We have around 1,000 noisy qubits to deal with. Can you fit your problem into that space? But if you can, it's far superior. And I just kind of want to touch that, with superposition, you're evaluating all the states in parallel. Real parallel computing. A classical computer, we conduct parallelism by basically running on different computers. Okay, now it might be on the same chip, but we're running on different computers. Then we have to try to merge those results and understand everything that has all that overhead. Quantum computers are truly parallel. They're actually conducting all these operations at the same time. So interference, oftentimes we're going to use interference to our advantage, where we have these waves and we can use something like the Grover's oracle that I talked about earlier to mark a certain wave, and we can allow basically the waves of all the others to cancel each other out. You know, if you have a peak and a trough, it cancels out, but if we amplify the answer we're looking at, it'll basically set all other states to 0 and the desired state to 1. You know, and that's the aspect of interference. And the quantum speed up is just so huge with that hyperparameter optimization or the logistics optimization workflow that we're just able to so quickly search so many states. All right. So those are the basics of what I want to talk about today. A little bit of a lighter, leaner thing, because next week we're going to go into some actual implementation. And it's going to be a little bit less slides and a little bit more of the notebooks or the simulator with Qiskit, which is the Python implementation of working with quantum computers. And there's also Chasm, which is on that slide there we go. Chasm is what I was writing over here to implement those gates. And if you're wanting to get your feet wet with quantum, go to IBM and get on this playground, because you can actually drag and drop gates. There's lots of tutorials on YouTube. They have tutorials on IBM. IBM, Microsoft, Google, they're all dying to get people who know how to operate quantum. They're putting these resources out there because we need more people who understand how quantum works. And so they've made some great tools where you can visually interact with how a gate affects the state. Yes, yes. Yeah. So, you know, simulation will work at the speed that, you know, a local machine can work. You can simulate it on your computer. Now, whenever I submitted this basic Grover's algorithm, okay, you basically add yourself to a queue on the quantum computer and wait for around 30 minutes before this little simple thing was uploaded. It ran in 3 seconds, and, you know, shot me back my answer. But you are running into that, where most of the time I spend whenever I actually want to run on a quantum computer is waiting for access. Now, here's the thing: if you're requesting more qubits or a larger algorithm, you know, they're going to estimate how long it's going to take your algorithm to run and how much resources it's going to allocate. And they're going to fit you in where they can. But if you're working on a real problem that's going to take some computation, you know, don't bet that I can submit it and it's going to instantly be done. There's just too much to say. What's that?
Data. It just completely miss the data part. You have to put some task.
Yeah.
Together as a package. Like this is the kind of simple algorithm.
Yeah, yeah. You're going to have to encode your data into quantum. And so with Qiskit, what you might do is they have operations. I take my data, and so it's like, this is a really simplified Grover's algorithm. If I actually had the database that I was searching for, I would have to encode my samples into a quantum bit, ones, zeros, up, down, and then evaluate it. Okay. So that's one of those things of that, like, you have to understand that with quantum, we can't just like send it a 1 and 0. We're actually going to have to manually encode those states. Now, I say manually encode. There's libraries that exist that they will perform that operation for you. But you have to understand that turning your data from classical data into quantum qubit data is going to involve some of that quantum computation. Yeah. Then, all right, a couple other things I wanted to go over is, last week I put a basic implementation of using Qiskit to implement quantum algorithms. And so if you have time, please go on to GitHub. There's QR code over there by the coffee table if you want to scan it to get access to GitHub. But you're going to import your necessary libraries, okay? Or install your libraries, import the actual services you want. And for the first two examples, I used a simulator. All right. And so I say that I want to, right here, you see these lines that are, I don't want to run it on the quantum computer yet. So I use the channel IBM Quantum. Okay. And I use that later when I actually run on a quantum system. All right. So I create a basic quantum circuit with 1 bit. So I have, a 1 qubit quantum circuit that I create. I apply a Hadamard gate to put that in the superposition between 0 and 1. And then I ask my simulator to measure that. Okay, my simulator will even draw the qubit for me, what my system looks like. I have 1 qubit, I apply a Hadamard gate, I perform a measurement, and I put that to a classical bit. Then you can run your system and designate how many shots. That's iterations in quantum speak, but how many times we want to run this algorithm. And so on my simulator, I ran it and I ended up with, this distribution. And quantum in true superposition would expect around 50-50. But, you have to realize that with the indeterminacy, it's going to be slightly offset. The more shots you run, the closer this is going to come to that 50-50. It's those basic probabilistic things. You flip a coin 5 times, it might be all heads, but as that n increases, the probability of a 50-50 chance drastically increases. Okay, and then I talk about how we can entangle bits. Okay, I use the Hadamard gate, put this bit in superposition, and then I use a controlled NOT gate to entangle qubit 1 with qubit 0, and then perform a measurement. And so I do my number of shots, and I see that I have qubit 00 and qubit 11, about 50-50 shots, but there's no 0, 1, or 1, 0. If the superposition of the first qubit collapses to 0, so does our entangled qubit. And then I took the same system and I ran it on a quantum computer. And there's tutorials. It takes a little while to understand, but you have to designate that, okay, my backend, I put service.least busy. Hey, whatever quantum computer has the most space, please run it on that. Okay, and then I have to generate some things that for access to that, and you'll have to create a quantum token, but IBM will just give it to you for free. Whenever you sign up, you can get a quantum token, and you can put that in your thing. I think it's around 10 minutes of compute you get for free. Which on quantum, if you're judicious with it, it's quite a bit. Okay, and then I ran that, and on the quantum system, we see some of that uncertainty. Okay, we largely got 0, 0, and 1, 1. But in a select handful of cases out of the 1028 or whatever runs I did, some quantum noise or classical noise interfered and actually flipped the phase of one of those gates before the measurement. Yes.
Did you compare the time?
Oh,
Similar code.
yeah. I wish I would have done that. That's great. But I can tell you that on the simulator,
Yeah.
I sat there for, it's a really big system, but I actually had some time. I had to sit there 4 or 5 seconds before I got the result.
Yeah.
Now this was sent to the quantum computer, and you're sitting there. You can see waiting for compute, right? Gaining access to compute, and then instantly spit back the answer. But no, I didn't specifically run an instance with time. But it's going to be. But also, you have to understand for this operation, I'm showing the mechanisms of conducting this, but putting a bit into superposition or entangling a bit, you're not going to see that huge quantum speed up. Yeah.
For the hardware, how many? I'm not sure RTM current state of art. How many qubits can?
Their best system, I think, is above 1,000.
Oh.
Yeah, but with my access, I think I can have up to 300.
I mean hardware, not simulation.
No, real. I'm saying that with just as a basic user account with IBM, Okay, I know they have computers capable of 1,000, and for pricing on that, you have to contact them directly and discuss their needs. They don't just have a menu to select from, which makes sense given the scarcity of the resources. But as a just, I want to play with quantum. I believe you can have up to 300 qubits, and you get about 10 minutes a month. So, I mean, yes, sir.
For the problem that you're trying to simulate, you need for the wind field to see how.
Yeah, so this is just a toy problem. I'm just showing that you can angle qubits and the results that you'll get, and that you can place qubits into position. Earlier, that black screen that I had, that was Grover's algorithm. And so that was an at-real search algorithm. Now we're searching a space 4 in that toy problem. But I hope you all understand, but I didn't want to waste a bunch of time for visualizations. But I wanted to show how simple it is really to implement these things.
Yeah, what is your
So here my input is I take a qubit, put it in superposition with the Hadamard gate, entangle a second qubit with that state, and form the recipe.
Oh, just to simulate it.
Yeah. Well, I mean, this is one on real hardware, but it's a very basic. But I just kind of, for anyone who's interested in it, I wanted to show a very simple entry. Okay, you can place these in superposition or form entanglement. And the Grover's algorithm is also shared on the GitHub on how you implement that. Similar to what I was saying before, I implemented the basic algorithm. You would have to encode your search space in that quantum hardware. I just wanted to show, like, hey, here's the search algorithm. Here's how simple it is to implement it. Whether you drag and drop, whether you code and chasm, whether you code and Qiskit. Yeah. Does that answer your question? Anybody else?
So the qubit allowed, like a term, the qubit is allowed for the frequency. Are there any credit or some?
Yeah, so you have to, if you want more than the 3 access, you have to contact IBM. You have to contact them for pricing. I haven't done that.
So free is free account usually for this stuff.
I think you get 10 minutes up to 300 qubits. Yeah. Yeah.
Is that 300 qubits per month or like per?
Well, I mean, qubits is the amount of resources you're access to, but you get like 10 minutes a month.
Okay.
Yeah. Which, I mean, you have to understand what they're providing is a playground for you to get used to the things. There are perhaps some problems you can solve with that, but it is kind of limited on how much you can accomplish. They don't want everybody just using their systems for free to solve their problems. But yes, sir.
So is there any other language where we can mount the qubits and for the learning purpose?
Yeah, so right now, pretty much every person with a quantum computer has their own programming language they've developed for it. There's also different programming languages that have been developed. I talked about that in the first session a little bit. There's Microsoft Azure, there's Google Quantum, there's IBM Quantum. And so IBM Quantum, which is what I decided to work with, just because it seemed to have the most operating at all levels of abstraction. If you want to do machine learning where you're not making manual quantum circuits, you can. If you have an idea for a new algorithm, you need to make your own quantum circuit, you can. So it's what I saw was it seems like different quantum providers have tried to specialize in different areas of that abstraction level. And IBM had the most broad-ranging aspect. So I started with IBM. IBM has Qiskit and Chasm. So Qiskit's a Python implementation. You import it in a normal Python notebook, and you can manipulate quantum circuits and run them. Chasm has more of a C++ feel.
There are a few other options. If you're not into circuit design,
Yeah.
Can you add?
Yeah.
Class IQ, there are more hardware. So.
Yeah. And that's the aspect. If you're wanting to get into this space, I highly recommend. I think in my preliminary search, I found 10 or 15 different quantum programming languages or providers. So there are some that are very specialized to machine learning, very high level abstraction. There's some that are more on the quantum circuit. There's some that are more cryptography or photonic quantum computer based. And so you have to select what makes the most sense with you. I went with IBM because it's one of the most popular and it provides the options at the different abstraction levels. They do have machine learning libraries. They do have the quantum circuit level libraries, and it's really popular. So that's why I went with IBM. Yes, sir.
I remember also last time you talked about there being desktop quantum computers available. How doable or like is it an acceptable challenge to try to set up a quantum computer at your own house? How acceptable is that as a challenge?
So here's the thing. I read about it in passing. I'm a little doubtful on how good that system can be. When we're talking about near room temperature operation, that's a lot of classical noise being injected in the system. I'm sure they're very limited on the qubits. Right now, I think it's a novelty.
I probably right. I don't think that stable on the computer is nowadays.
I've seen it
on the yeah. I probably news, so I think that there's probably some misinformation.
Yeah.
Because quantum computer nowadays mainly relies on two technologies. One is the ultra low temperature. People can actually circuit. The second is trapped ion. So both are actually need to have reasonably sophisticated instruments. So I don't think for people to use we can have fulfill probably the next 10 years.
Yeah. I agree.
But on the other hand, because quantum computer is so powerful, so you really need to put, I think eventually could replace the main computer. Have a center with a house of the computer center. So you not need that everybody carry a quantum computer. No. Yeah, I think the prediction is with the quantum computer eventually, you are not out of computing power. You are out of the information you want to process.
Yes. And that's a good point. And it's like the GPTs and the large language models are making a lot of strides, computation, but it's like the big limiting factor they have, they're out of information. They scrape the internet. And so I think that's the aspect we're going to see with quantum computing as well, is that they're going to be very efficient, but like you said, at some point we're going to run out of information to, anybody else?
Do you have anything for similar to hands-on or this is
this was the information for seminar 1. Yeah, that's a good question. What did I have? Please get out of my way. See. I'm having trouble signing in the GitHub for now, and I'm not going to make you all wait. But if you go to the GitHub under Seminar 2, you can access that Grover's algorithm playground that I implemented. You can go in there, you can play with things, drag things around, and see how it works. Okay.
give us some idea about next seminar?
Yes. All right. So next seminar, I'm going to talk about actual instantiations of quantum AI, what that's going to look like from architecture. I'm probably going to talk about QSVMs. I'm going to talk about instantiating layers in neural networks. And I'll also develop a little toy system that we can play with that I can show you guys. So we're actually going to get into what does quantum AI look like? What are the tools that we use? And then looking even further in the 4th seminar, we're going to actually specifically talk about graph neural networks and some of the great tools for quantum algorithms that we can apply to those, where we can actually do the spectral analysis and matrix inversion, these really powerful tools. for solving non-Euclidean spaces.
Sounds good. Thank you so much.
Thank you. Thank you. All right. Let's see. Housekeeping. If you're in Dr. Slow's class and you have not signed in, please do so.